All right, moving along, example number 4 from 7.3. I always found the way that the notes did this question a little bit annoying. I don't think it's very intuitive, is my problem with it, is what the notes, and if you've taken a look at the Keto notes, I'd recommend it. But it's basically, it moved the 12 to the other side. And we get that the absolute value of 3x minus 4 is equal to negative 3. And that's a problem because absolute values never yield negative numbers. And I'm a big fan of graphing. So if we did graph these these two sides, so I'm just going to put y1 in red over there. The absolute value of 3x minus 4 looks roughly like this. Right, give or take. I'm not going to worry too much about the exactness of the graph. We could use our calculator for that. And then if I graph the right-hand side as y2, y2 equals negative 3 is all the way down here. Now, really importantly, if I look at the graph of y2 and y1, I hope we all agree that they're never going to intersect. Now, what that means mathematically is there's no value of x that causes the left-hand side to share the value with the right-hand side. There is lots of other ways to do this. If you did the normal technique, which I'm not going to show up here, if you used our normal technique of the absolute value of a positive and the absolute value of a negative, you would get that both answers don't verify correctly. Really important that I think it is valuable to know a couple of different techniques. The graphical technique that I've done over here is very handy and typically very quick to do on the calculator as well. A bit of a short example, so I'm just going to kind of roll example 5 into that. This one is tricky because it has a quadratic expression inside the absolute value. But it's really important to not let that throw you off. We're not going to do anything different. We're going to talk about, okay, when we're solving the absolute value of a positive, and then when we're solving the absolute value of a negative. This is how all absolute value problems, or equations I should say, should start, because it is always worth considering, how do I solve this? And in an absolute value, you don't. You change it so it's non-absolute value. So I'm going to do both of these one after the other. If the inside expression is positive, the absolute value does nothing. If the inner expression is negative, the absolute value multiplies it by a negative 1. Now, let's solve these. They are quadratic, so we need one side equal to 0. I'm going to subtract 1 there. I get that x squared minus 2x minus 1 is equal to 0. And we run into a problem because we would, I hope, try to factor this as a quadratic. I need two numbers that multiply to negative 1 and add to negative 2. There are only two numbers. Sorry, that should be a negative 2. I said negative 2, wrote positive 2. There's only two numbers that multiply to negative 1. Positive 1 and negative 1. That adds to 0 all the time. So that does not factor normally, which means we would have to use our quadratic formula, which is going to take up a little bit of space, but that's okay. When we use our quadratic formula, I'm going to write underneath that the a parameter is 1, the b parameter is negative 2, the c parameter is negative 1. So the solutions of x are negative 2 plus or minus the square root of negative 2 squared minus 4 times 1 times negative 1, all divided by 2 times 1. That's our quadratic formula from chapter 4. Very important that you don't let that go by the wayside. You have to make sure you're capable of working with that. And moreover, you have to be able to simplify the answers. So I'm going to get that x is equal to 2 plus or minus the square root inside the discriminant. I'll just kind of do that right here. Negative 2 squared is 4. Negative 4 times negative 1 is positive 4. So we have 2 plus or minus root 8 over 2. When we simplify that radical, it's 2 plus or minus, again, I'll just do that over here, that root 8 is the square root of 4 times the square root of 2. So it can be written as 2 root 2. Again, take a look back to your chapter 4 stuff if you're struggling with using the quadratic formula. We have a lot of good quality practice within that section. So 2 plus or minus 2 root 2 over 2. Every term in the numerator is divisible by 2. So I get that x is equal to 1 plus or minus root 2. Now, I'm going to cheat a little bit here. I'm not going to show the verification for this. If you're going to verify this on your calculator, I'd honestly recommend, putting this in first and then using the decimal version of those numbers and then making sure that you're using the full decimal. But both of those do work. And so we get two answers. X is equal to 1 plus root 2 and x is equal to 1 minus root 2. Both of those are valid solutions, and I'll show you the graph of the solution at the end here. Unfortunately, and that's what makes these questions difficult, is that's only half the battle. We have solved only when it's the absolute value of a positive number, so we have to solve when it's the absolute value of a negative as well. And to do that, we have to distribute that negative on. I'm just going to do this in red to hopefully not kind of mix the two techniques up. So negative times x squared is negative x squared, and negative times negative 2x is positive 2x, and that's equal to 1. Now that's still quadratic because we have an x squared and an x. We need to get one side equal to 0. It does not matter which side. So a lot of students just kind of default to moving the constant over, subtracting 1 from both sides. But I really like having my x squared positive. So I am going to move all the variables to the right-hand side. And what I'm left with is that 0 is equal to x squared minus 2x plus 1. And it gets a little bit friendlier here. It's a slight difference, but because this quadratic, we need to find two numbers that multiply to positive 1 and add to negative 2. We are going to use negative 1 and negative 1. That satisfies both of those conditions. So this does factor nicely into x minus 1 times x minus 1. This gives me, two solutions. Either x minus 1 is equal to 0, that's my first factor, or my second factor, x minus 1 is equal to 0. Those are the same thing, so we get that x is equal to 1. Now, if you go back and put that into the equation, that does verify as well. And one of the things that and I'm sure Ms. Pankos would massively appreciate, is that if you do a quick little kind of, summary of what your answers are. So I have that x is equal to 1 minus root 2, positive 1, and 1 plus root 2. It's really nice for us to see that you understand that there's three distinct answers. Really importantly, that when you're finding those answers, if we ask for exact form, you're leaving it as 1 minus root 2 and 1 plus root 2. If we're asking for approximate form, 1 plus root 2 is 2.41 with a bunch of other decimals after the fact. Okay, the last thing I want to do here is I want to show you the graph of this just so we can talk about it. And I'm just going to bring up your calculator to do that. Okay, so grab your calculator and we're going to put both sides of the equation in. We showed that in 7.2. So you go to the math menu, over to number. It's the absolute value of x squared minus 2x. That's the left-hand side, that's y1. The right-hand side is just positive 1. Just to make sure we're all looking at the same thing, I'm going to go to my kind of default zoom, which is zoom standard. And then it produces this graph for us. So the blue graph is the absolute value of x squared minus 2x, and then the red line is x equals positive 1. Now, it's not very easy to see what's happening here. So I think it is valuable to know that all we have to do is we just have to change our window settings. So because I want to look at this region, and I'm kind of circling with my mouse there, hopefully you can see that. Because I want to look at that region closer, I hope it's clear that I can reduce all of the max and mins, and I'm still going to get a good look at that graph. So what I would recommend is use some kind of routine technique, and I'm really just going to half them, and we'll see if that gives us a good look. So I made everything half as big on the y min and the x min and the x max and so on. When I graph that now, I get a bit of a better look at what's happening. I think this is probably all you really need to do, because hopefully it's pretty clear that this is hitting the graph. And maybe this needs a bit of a better look, but we see that it's hitting the graph, and it looks like it's hitting at 1, maybe 2 or 3, and then again 3 or 4 at the end, just because we don't really know what's happening there. Your calculator has a function called zoom box or zoom in. I'm going to use zoom box, and it's really going to act as if you were on a computer, and you're going to hit the corner of the box and then use your cursor to basically just kind of encapsulate whatever you want to look at closer. And I just want to see a little bit more what's happening here. Now we have the algebraic solution, so we can kind of cheat. X equals 1 right here. So it's really only hitting in one spot. But if I do use zoom box, I can see a much, much more zoomed in version. And we're going to see that red line just touching the quadratic at the top there. And I'll hit the trace to show you that only occurs when x is equal to 1. At x equals 1, both of those graphs have the same value. So that does count as one of our solutions. Never a bad idea to use your calculator to find these. There is a pretty major downside though, and I'm just going to go back to zoom standard to show you that downside. The calculator never gives you exact value. So when we had 1 minus root 2 and 1 plus root 2, we knew the exact value through our quadratic formula. I'm going to find 1 plus root 2 right there on the graph, and the way that I do that is second trace. It's the intersect, that's option number 5. And then I'm going to put my cursor on the intersect that I want to find. Now on this intersection, the first curve is y1 in blue, the second curve is y2 in red, and the guess really doesn't matter, but if you put the guess on a different intersect, it'll calculate that intersect. So we want to find it kind of right there. and it tells me the intersection is 2.4142136, blah, 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 blah. Now, if you're doing a multiple choice, worst case, you check if that matches the decimal that corresponds with your algebraic technique. And we see that that is the exact same number we had there. Now, I don't know how you would ever go from a random decimal to the radical. So it's really important that despite the fact that the graphing calculator can do this so quickly and so reliably, you still have to know how to do it algebraically, because we often ask for exact values to ensure that you're not just plugging things into your calculator and basically, not learning the math.